Okay, so for this next question, we're doing fatty acid synthesis. And all this is just putting in fatty acids together and elongating them. And this occurs in a series of 4 steps. We have condensation, then reduction, dehydration, and then reduction again. So knowing the order of this is super important because it allows you to understand how this process is actually occurring. So I'm drawing acetyl ACP, and we're adding it with malonyl ACP. So I'm just going to refrain from drawing hydrogens just because it takes too long. So we have acetyl, ACP, and then malonyl ACP. So through this process, what happens is that the shared electrons between the oxygens are actually going to be removed once they are linked together once malonyl is linked together with acetyl ACP. And this is occurring through the process of condensation. So this is a spontaneous reaction, but it doesn't require the input of energy, which makes it endergonic. So we're removing the CO2, which is what I circled in green, and we also have ACP. We're removing one of the ACPs from the group. Specifically, it's the one from acetyl ACP, so I'll circle that as well so you guys know which one is lost. And through this condensation reaction, we form aceto-acetyl ACP, which is a structure that looks like this. So we're just linking the two together. You always want to count also from the carbon that's attached to the thio group. So this is going to be 1, 2, 3, alpha, beta. So we have that group. Okay. And then next we have reduction. So we're adding in NADPH, and it's getting oxidized to NADP+. Recognizing that we're using NADPH for this pathway is also important. And we have the reduction of this carbonyl here into an OH group. And the electrons to this specific structure is coming from NADPH. Okay. And then that's when you have hydroxybutyl ACP. So next we have, so that step actually was reduction. And this next step is the dehydration step. So we're removing water. And the water is actually removed from the OH that's here, as well as one of the hydrogens that are here as well. And you get this group here. So now you have a double bond. This double bond is between the alpha and beta position and is called crotonyl ACP. Okay. And then the final step is reduction. And through this, you use NADPH that you generated earlier from the first reduction step, and you make the NADP plus again. Oh, I'm sorry. You make NADP plus in the reduction in both reduction steps. Okay, and then you have the group between the alpha beta is no longer oxidized. This is a sulfur right here. And the hydrogen from the NADPH is actually now on this carbon right here. And yeah, that's what you have for this pathway. Okay, so for this next, and so you'll need to know the 3 different types of equations that are related to photosynthesis. The first one is this general equation right here, and that's just the general equation for plant photosynthesis. There is also another one, which is the oxygenic photosynthesis, which he has on his slide, and that's when you're using oxygen as the product formed by the oxidation from the electron donor. You also have certain types of bacteria don't use oxygen as their main source. Instead, they use sulfur, for example, like cyanobacteria, and they use the anoxygenic photosynthesis. So they'll use the H2S instead of H2O as the electron donor bisulfur bacteria. So just make sure you're familiar with those 3 different types of equations. Also, you want to familiarize yourself with characteristics of the chloroplast. So know that the chloroplast is a double membrane organelle, and it consists of the inner membrane, which surrounds the stroma. And you can kind of think of the stroma as the matrix in the mitochondria. They have similar features. It's actually the site of carbohydrate synthesis from CO2 using ATP and NADH formed in the light reaction. And in the stroma, there is a membranous sacs, which are called the thylakoid. And the thylakoid membranes are the location of the light reaction in photosynthesis. So know the inner membrane, the outer membrane, the thylakoid membrane, the thylakoid lumen, and know the characteristics that Dr. Thomas has in differentiating between the mitochondria versus the chloroplast. Also, another thing that I wanted to address that I didn't put on the study guide are the relationships in quantum mechanical description of light. So you have the general equation of energy, and this is the amount of energy that's associated with each photon. So you have H, which represents Planck's constant, and you have nu, which is the frequency in cycles. You also have these 2 equations. And so understanding the relationship and being able to plug in is really important for this. I doubt there's going to be any types of calculation. But for example, if you had that lambda was decreasing, a question that could be asked is, what is happening to your energy? So they're inversely related, right? Energy and lambda are inversely related. Therefore, if lambda is decreasing, energy must be increasing. So just knowing those types of relationships is really important for this final. Okay. So next we're going to get into chlorophyll. So make sure you're familiar with how the structure of chlorophyll look like. So knowing that magnesium is the center, right? So remember when you were learning about hemoglobin, you had iron as a central element. In this one, you have magnesium, and it's used for the proton motive force. Okay, so noticing that magnesium is surrounded by a series of pyrrole, along with a chain of carbohydrates, is an important characteristic of chlorophyll as well. Also, you want to be able to recognize beta carotene. So beta carotene facilitates electron transfer. There's a slide in Dr. Thomas's lectures in which he shows beta carotene and its role in photosynthesis. Okay, so let's start with the characteristics of photosynthesis. So we have 3 different compartments. So we have the stroma, the thylakoid membrane, and the thylakoid lumen. And the thylakoid lumen is the interior of the thylakoid. And so you have light coming in beginning at photosystem 2. So we have 3 different compartments, not including the ATP synthase. But you have photosystem 2, which is where it begins. Then you have cytochrome B6F complex, and then you have cytochrome 1. So light comes in, and it hits the P68, and this is the increase in free energy. So we have an increase in free energy, a P680 gets excited, and you have the transfer into acceptor gaining electrons. So the P680 transfers the electrons into the immobile electron carriers. The pH, I forgot what this is called, but I know it's in his slide. And then it gets transferred into QA and QB, and then it gets sent to the cytochrome complex. So the Q pool is actually here in this specific, I'll highlight it, this specific region right here. So you have the transfer of 2 protons and 2 electrons, and the protons actually get pumped into the thylakoid lumen. At the same time, you have this PC, which is the plastocyanin, which transfers single electrons to photosystem 1. And in photosystem 1, you have light comes in, hits P700, the photon gets excited, and then the electrons are transferred onto chlorophyll 2, which is A0, chlorophyll 1, which is quinone, the 4 iron sulfur clusters, and then FD. And then that gets transferred to NADP plus reductase, which reduces NADP plus into forming NADPH, and that actually powers the ATP synthase. So as the hydrogens are in the thylakoid lumen, we have that they enter the ATP synthase, and ADP plus inorganic phosphate gets actually converted to ATP plus water, and those are saved for the citric acid cycle. The Calvin cycle. So the flow of electrons from H2O to NADP plus generates the proton motive force. So we have H2O, so as electrons are flowing from H2O to NADP plus, that's actually generating the proton motive force. Okay, so also in his lectures, he goes into the specifics of the ATP synthase, but knowing the general concept of photosynthesis, I think, is a good place to be.